Hello everyone, my name is Chirag Patil and welcome back to my YouTube channel. So in today's video, we will understand AlexNet, which is CNN architecture, right? So first of all, we will understand introduction of it, then we'll deep dive into the architecture and then we will implement it using the PyTorch. Okay, so let's get started. So first of all, AlexNet is one of the most influenced deep learning models in the field of computer vision. As I say, it is a CNN model, right? So it is primarily known as success of image classification task. So why it is called AlexNet? So one of the author of it, it was Alex, right? So basically the team of Alex, Ilya Sutskever and Geoffrey Hinton work on this model and implemented this AlexNet, right? So basically its title is like ImageNet classification with deep convolutional neural network, and it was published in 2012. So there is an ImageNet data set which is used as a benchmark to evaluate your classification model or computer vision model, right? So AlexNet in 2012 got the first rank with top error rate of 15.3, while the second model which get the second rank has the error rate of top 5 error rate of 26.2, which I would say almost double, right? So it is like outperforming all of the model in that competition in 2012. So we will understand the architecture of it and then we will implement. So let's first of all understand the architecture. So if you see the paper, they have already mentioned everything, right? So what will be the kernel size and how many layers would be there, right? So here they had mentioned. So this architecture can be look like a difficult to understand at the first attempt, right? But they have explained here everything. So what I did, I just compiled these two paragraphs from the paper into this diagram, so we can easily understand. So here I am assuming that you know what is the convolutional operation and how convolutional operation works. Okay. So basically, if I talk about the architecture of AlexNet, it has simply 8 layers. The 5 is convolutional layer and rest 3 are fully connected layer, or you can say linear layer as well. Okay. So first of all, we will start the architecture of the input size will be 227 by 227 by 3. 3 is basically the channel which will be RGB, right? So RGB image with input size 227 cross 227. So if you see in the paper, so they had mentioned 224 by 224 by 3. Okay. But if you see next part of it, when they are applying the numbers, right? So after applying the convolutional layer with 11 cross 11 kernel size and stride of 4, they are receiving 55 as an output size, right? But if you apply this same operation on 224 image size, you will not receive this number. So that's why people are using 227 as an input size to follow the same architecture with the same number of output size, right? So we will also use 227 as an input size, okay, when we will implement it. So if you see, first convolutional layer will have 11 cross 11 size kernel and stride is 4. So of course the output will be a lesser in the dimension, right? So first of all we will start from 227 and then we will receive 55 cross 55. Then we will apply max pool, right? So size will again decrease and we will receive 27 cross 27. So here if you see padding, there are two words like valid and same. So when I write valid, valid means we are not applying any kind of padding. The output will be compressed or you will receive a smaller size output, right? When you are applying padding is equal to same, that means we will apply the padding and we will receive the same output size. Okay. So if you see in the after applying max pool, we receive 27 cross 27 cross 96, right? After applying convolutional 2D with padding same and stride 1, we had received same 27 cross 27. The channel will different because we will use a number of kernel is a different number, right? Whatever it suggests in the paper. You will get better idea when we will implement it, right? So same, if you see the 2 convolutional layer followed by the max pool and then 3 convolutional layer without any max pool. At the last we are applying the max pooling. Sorry. Okay. So at last we are applying the max pooling and then fully connected layer or linear layer. So as an activation function, the AlexNet use a ReLU. Okay. So these are the same line you can hear as well, right? So if you see the this line, the third, fourth and fifth convolution layers are connected to one another without any intervening pooling or normalization layer, right? So what we are doing here, the same thing, right? So this is the summary: 8 layers, 5 convolution, 3 fully connected, and some of the key innovation which are used in the AlexNet, which makes it better than other in the 2012, right? So first of all, they are using ReLU activation function, right? Before that means before AlexNet in 2012 or before, when people are using convolutional layer, they are using sigmoid or 10H kind of activation function, and we know that sigmoid and 10H are prone to a vanishing gradient, right? We can face the vanishing gradient problem. So ReLU can avoid or mitigate that problem at some extent to vanishing gradient, right? Second thing, the AlexNet was one of the first neural network which utilized the fully GPU, right? It was trained on NVIDIA GTX 580 GPU. So if you see here, the diagram is shown also that kind of thing, right? So if you see here, there are two parts of this diagram, right? So first of all, let's say you are using number of kernel 96, right? So 48 kernel will be processed in one GPU, and the second 48 will be processed in the other GPU, right? So they are also like divided this diagram in two parts as they are using two GPU, right? So if you see here, like we are using 256 kernels, and 128 will be processed in one GPU, other 128 will be processed in another GPU, right? They have mentioned the same thing here as well, right? The responsibilities between the two GPUs, right? So this is one, and they are using the dropout as a regularization. So dropout is nothing but basically dropout layer will take as an input like 0 to 1. It will be the probability of that much neuron will be provide output as a 0, right? So for example, if you are passing 0.5 as a dropout number of a point, right? Then means 50% of the neuron will be blank, or it will be provide the output as a 0, and it will not provide any kind of significance in forward pass, same as backward pass, right? Backward propagation. So that means we are not relying for particular part that on that neurons, right? So this is basically dropout, and it will help to regularize the model. Okay. The second thing is data augmentation. So data augmentation techniques, they are used like randomly cropping the image, flipping the image, some color perturbation techniques are there. So they are basically converting the images in some kind of different way. So let's say there are one image, so you can flip it. So meaning will not change, but image will be different. So that means you can increase your input data as well, and providing as much as possibility for that image, right? So model can understand in a generalized way. So it also used to overfit, prevent the overfit or generalize the model, right? So these are the few points which are used in AlexNet. So let's move and implement it, right? So for implementing, I will use one library which is Torch, and there is Torch view I am installing because we can visualize the model at the end. Okay. So here I had written one formula which is nothing but like calculating the output after applying the convolution operation. So here if you see in the table, we had provided the output dimension, right? Like for first we will apply 11 cross 11 kernel size for stride and padding valid. We will receive 55 cross 55 cross 96 dimension output. Okay. 96 basically a channel, or you can say number of kernels. So how this 55 come, right? So you can use this formula. So this is nothing but input size minus kernel size plus 2 into padding and divide by stride plus 1, right? So this is same. So we will calculate for a few layers so you can get better idea. So let's run this. Okay, so we already imported the necessary libraries. Now let's build a class. Let's say class is AlexNet. Okay. So let's say an n.module. Sorry, m will be capital, right? Now let's call this constructor of that class, of superclass I would say, in it. For this we are just doing just class implementation, right? So now let's start some model. Okay, so we are basically dividing this code into two parts. First will be the features, which we will use 5 convolutional layer which is defined here, right? And then this fully connected layer will be in the next model. So we are just basically implementing 2 neural network here, and we will combine them. So let's say self.features will be, so I'm just creating sequential model, sequential, okay. Oh, sorry, so there we forgot to write init method, right? Let me write, in the constructor of this class we should call the constructor of inherit class, right? So let's say first argument is self, and the second we will use like class, let's say called number of class, right? Number of classes. So as we know, this model was basically trained on the 1000 class, so we are just applying here number of classes 1000, and let's provide the typing as well, right? So it will be the integer, and let's say dropout. So dropout will be float, as I say it would be 0 to 1, so we will provide default 0.5. okay, so this is about the AlexNet input. So now let's build this. Okay, so this will be the inside this. Okay, so now our task is to create the convolutional model. Okay, so now let's say first will be nl.con2d. Let's use this. So what it take out as an input, right? So first you can see this is the input channel, which is the image channel first input. So in our case it will be 3, right? Because we are passing input as an 227 cross 227 cross 3. So let's say I'm writing here argument as well, so it will help to understand, right? So for our input channel will be 3, and output, let me write, output channel would be 96. Let me write it this way, right? It would be more visible. So let's say kernel size will be, as I know, 11. Let's say stride is equal to 4, and padding, we are not applying any padding, so let's say valid, right? So this will be our first convolution layer. So if you see the diagram, we are doing same thing, right? First convolution layer will have kernel size of 11 cross 11, stride will be 4, padding would be valid. Simple, right? So here we are doing same thing. And output channel 96. Output channel is basically defined here as well. If you see in the paper, you can see the second convolution is here, first would be somewhere here, yes, here. So you are applying 224 is the input shape, right? But as we discussed already, we will use 227 and with 96 kernel of size 11 cross 11. So we are doing same thing, 96 kernel of size 11 cross 11, right? So now let's just check what will be the output shape here, right? So I can say calculate output shape. Our input shape will be 227, kernel size is 11, stride will be 4, and padding will be 0. That means no padding, right? Yeah, so we are receiving 55, which is same as shown in the table, right? So we can write here output shape will be batch size, comma. So in whenever you are dealing with a torch, there is the output will be channel first, right? So we should write channel first with 96 and then 55, comma 55. When we are passing the input, it will be also like this. Let me write that. So input shape will be here, let's say batch size, comma 3, comma 227, comma 227. So basically a channel first. So in TensorFlow by default they are using channel last. That means in that it will be 227 cross 227 cross 3. But here we are using channel first. So it will be like this. Okay. So now as we know, it is using a ReLU as an activation function, right? So let's apply a ReLU. So it will be like this, ReLU, and we are applying in place is equal to true. So it will not return anything, but it will change the actual value, right? And then as you know we need to apply max pool 2D, right? So let's say max pool 2D, and in also like we need to apply kernel size. For almost all the max pooling layer in this architecture, we use kernel size of 3 and stride of 2. This is a standard, okay, in the whole architecture. So here would be comma is remaining, okay. So let me write here, right. So this will be our first convolution block. So after applying the max pooling, we will also get a smaller output size, right? So here output size will be, so here you can check a same thing, right? So let's say now our input size is 55, our kernel size is 3, stride is 2, and padding we are not applying, right? So now our output is 27. So you can see here as well. So we are receiving 27, right? So now it will be batch size, and now output channel will be same 96, because we are not applying any number of kernel in max pooling, right? So 96 comma 27, 27, right? So this is our first convolution layer with max pool. So now second we need to do same thing. So I am copying this and we will change the output, we will change parameters, right? So let me write here, let me say, sorry, second con layer, it would be first con layer, right? Let me write comma here, okay. So now if you see, when we are applying con 2D at the next time, our input channel is 96, right? So let's say 96, and output channel we need 256. So if you see the diagram or table, the next time, sorry, it would be 192, not 256, right? Okay, let me check what is it, right? Sorry, it is 256. So as you know, 128, 128, it will be 256. So there is some error here. Let me correct it, right? Okay, 192, it will be 256 and 256, right? So now it is changed. Now let's write our code. So it will be 256, kernel size will be changed to 3, and stride would be changed. The stride is basically 1 here, padding would be valid, and output will be changed. We will check what is the output, right? So now let's say we have our input channel as an 27, right? So let's say 27, kernel size is 3, stride is 1. So now it will be converted into 25. Now that 25, okay, there is something the issue. Okay, so when we are applying the next convolution layer, we did not require padding is equal to valid, right? It would be same, because the output size will be changed when we are applying max pooling. It will be not like this, okay. So here we will receive the same, let's say 256, 27 and 27 after applying the convolution operation. Just we are changing, the output channel will be 256 and output will be same, because we are applying padding is equal to same and stride is equal to 1. When we are applying the max pooling, it will be changed to here like 256 will be 13 and 13. So we can check that as well, like when you are applying 27, the 3, stride 2, you will receive 30, right? 13 basically. So 256, 13 plus 13, this will be our second convolutional layer, right? And we know first and second follows the max pool 2D, but from third, fourth and fifth are not connected using max pooling, right? So let's say I'm writing third con layer, and let's say nn dot con 2D and channels will be, now we need to, for third convolutional layer we need 384, right? Then 256, then 256. Okay, and this all convolutional layer will have same padding, right? So let's say input channel will be here 256, and output channel will be 384. Kernel size will be 3, stride will be 1, and padding will be same, right? And apply relu. Let's say in place is equal to true, right? So this will be our third convolution layer. Now let's write fourth con layer. This will be same. Let me copy it. Right, so here input channel will be changed as 384 because previous layer will provide 384 channel output. Then we need to convert it into 256. Padding will be same, and we are applying the relu. Now the fifth convolution layer will be the same as the fourth, right? So let me write here, fifth convolution layer will be, input will be 256 channel and output also will be 256. Okay, so if you see here the output shape, okay, so let me, I'm forgetting the comma here, it will be there. Okay, now it's perfect. So if you see the output shape, okay, so output shape will not change here. So when I'm copying, this typo is there, let me replace that, same. Okay, done. So here will be output will be batch size, and here is 13 cross 13, right? So as we are not applying any kind of max pooling or not applying any larger stride or padding is equal to valid, then output shape will not change. Channel number of channel will be changed, but image size will be same, right? So here will be output will be 384 13, 13, right? Same here, if you see the output channel is 256, and then it will be batch size, 256, 13, 13, right? Same here, the output channel is 256, so it will be batch size 256, 30, 13. Simple, right? So now after fifth convolution layer, we need to apply a max pooling. Here you can also see 120 and 128, that means 256 after 13 cross 13 size, 256 channels, and then we are applying the max pooling, right? So now let's apply nn dot max pool 2D, and we are applying, as I say, kernel size would be 3, strides would be 2, and this will change our output shape, right? So let's see what will be the output shape. So let's say, let's go here, let's say my input size is 13, kernel size is 2, and stride is kernel size is 3 and stride is 2. We are not applying any kind of padding, then output will be 6, right? So now output will be batch size, 6, 6, it would be 256, 6, 6, right? The output channel will not change, the size will change simply, right? So it will be 256, 6, so here you can see also the output is not defined here, but we are applying the max pooling simply. Okay, so this will work as a feature network for me. So convolution part is done here. So now we need to build a classifier section. So this is basically a whole one neural network, but I am just dividing it into this two part. So first is convolutional operation, and second will be fully connected layer, which can be called as a classifier as well, right? So let me write that code as well. So let's say self dot classifier, which will take first will be self. No, it is, we need to build sequential, right? And dot sequential. Okay, so after doing this, first of all we need to flatten this output, right? Which will be convert this 256 into 6 output size, one array basically. Currently it is in the matrix format, right? So that we can apply in the forward method when we are creating the neural network, right? We need to create one constructor and one forward method. Forward method is basically apply on the forward pass, right? So I'm not writing flatten here. Flatten we will write in the forward method. So now I'm just applying the classifier. So first of all we need to apply dropout layer as well, right? So let's say, let me write it here, and dot dropout will be, and dropout p means basically probability, we need to plus float. So we had defined above as well, right? So let's say dropout, which we had defined here in the construction, the dropout, which is default 0.5. Okay, so this is the dropout. Then let's say linear layer. Linear layer is nothing but a dense layer if you are coming from the TensorFlow, the same thing, right? So linear. So linear input feature will be, sorry, it would be in features, right? Let me check. Yes, it is in feature. So if you see, the input feature size would be after flattening this, right? So we can apply like 256 star 6 star 6, sorry, yeah. So multiplication of this three numbers, right? Because we will flatten this output. You can understand when I will define the forward method. Just bear with me, okay? So and let's say output feature, it is out feature. Out features will be 4096, right? Let's see the diagram or the table. Yes, we need to create 4096. Okay, so let's say 4096 and apply relu. In place will be true. Okay, so now let's apply second neural net, second linear layer. Before that, let's apply dropout. Okay, dropout p will be dropout same dot linear, and linear we need to feature, input feature will be 4096 as like a previous linear layer providing output feature as a 4096. So here in features will be 4096, out features will be 4096, right? Same, let's apply relu. In place will be true, right? And now we are just applying one linear layer, which will be our output layer, right? So let's say, sorry, let's say nn dot linear input feature, sorry, in features will be 4096, out feature will be number of classes, which we had defined 1000 because it was trained on the ImageNet dataset, right? So this will be our classifier. So we can apply the softmax layer as well here. So this is basically in activation at the end to classify each classes, okay, with the probability. but we can apply that as like in a training loop as well on the embeddings or the output which we receive from here. So you can do at any time. Okay, so I am just not applying softmax here because in the training function we can apply, right? So now let's define a forward method. Okay, so let's say define forward self. It will take out it will be basically a input, or you can say image, right? It will be like torch dot tensor, right? Tensor t would be capital, right? And it will also return also torch dot tensor, right? Simple. So now let's implement. So as I mentioned, like first of all we need to calculate this image features, right? So let's say features will be self dot features, and we will pass our x. Okay, our input basically. So now as we know, this will return our as a matrix, right? So we need to convert this into a single dimension array, or we need to basically flatten it. So we can write, not write the features, let's say x is equal to this, x is equal to, now let's say nn dot, or it will be torch dot flatten, right? Let's say torch dot flatten, we will pass x in 1. Okay, so basically it will convert into one dimensional array. So now x, let's say this flatten output will be passed to this classifier, right? Self dot classifier x, and this will be return x. Okay, simply. So it is created our AlexNet here. Let's run this, check if there is any error. No. So let me create the model, will be our AlexNet, right? Simple. So this is the model. Okay, so unexpected output. Okay, so it would be out, right? It is a typo there. So input channel, it will be out channel, and it will be like out channels, right? Let me check. Let's check what is the definition of it, right? Sometimes we can forget. Let's say torch con 2D. It is out channels. Okay, so there are a typo at almost at all place. Let's resolve that, right? So it is out channels, here out channels, here also it would be out channels, right? Channels. Okay, I think we are done. Let's run. Same torch.nn has no attribute con 2D. Okay, where I used capital D. Oh, it would be a small d. There are lots of typo I did, sorry guys. Okay, let's run. Okay, so now it works. So let's plot this to visualize we are doing a proper way, or we are receiving the proper output or not, right? So I will use basically this library which I had imported here, right? The torch view. So we will use draw graph. It will receive, it will take a model and input shape. Okay, so let's say draw graph, we will pass model. Let's say input size is 1227, and it is channel first, so we need to pass 3,227, right? And let's write expand nested is equal to true. So if we are using any nested model, right, as you know, in AlexNet we had used 2 sequential model, right? So it will plot each. Let's say true, and fail to run. See the error message, torch has no attribute flatten. Okay, so what we need to do here, torch dot flatten, let's see. Okay, so it is small f there. Okay, Now let's see. Okay, so it is returning the object, so we need to visualize this, right? So there is like visual graph. Yeah, let's see. Okay, so if you see here, let me zoom it little bit. Yeah, so if you see, whatever I had created in the table, we are receiving the same output size, right? First will be 55, then 27, then it will convert it into 13, and then 13 will be carried to the end. At the when we are applying the max pooling, it will convert it into 6. Then we are applying a flatten layer, which will convert this 256,6,6 into 9216, right? And then 9216 will be converted into 4096, and then 4096 will be converted into number of classes. And this is our output dimension, right? As we are passing here like one image as an input, 1, 3, 227, 227. So output will be 1, 1000, which is basically 1000 class, right? So let me reset it. So yeah, this is all about the AlexNet and how you can implement it using the torch, and you can now further it train on any image dataset, right? So if you have any query or doubt related to this AlexNet, you can write in the comment section. We can discuss there. And if you like my video, please press the like button and subscribe my channel for more content. Thank you.